Yeah, agreed. Okay, let's kick it off with our next talk. So we're starting to move a little bit away from the SNARK and STARK stuff and into other fancy crypto stuff, which I'm personally very excited about as well. So we're going to have John, aka Tux Pacific, talk about fully homomorphic encryption. Please give him a round of applause.
Hey, glad everybody can come to this after eating lunch. I'm glad you guys will fall asleep during my dry technical talk. So hopefully you're caffeinated enough to keep up. We got a lot of details to cover, so I'm going to kind of slide through a little bit what we're doing for the overview. So I'm going to be discussing a bit what exactly is secure computation, what technologies can be used for secure computation, things like MPC, Ts, trust execution environments, and FHE, as well as the shortcomings of each of these approaches, and the solutions for the FHE-based approach and what Nucypher has actually accomplished recently and what we are working on. So we'll be very quickly and briefly discussing just the MPC and T stuff so I can spend more time on FHE. So that way if you have questions, we can actually get through those. So let's dive right in. What is secure computation? Typically there's a requirement for privacy. In this case, there's parties, usually somebody needs to perform a some function f on some inputs, in this case x and y, and in this case there's usually a requirement for that privacy where the data x or the data y may not want to be revealed when you're doing some sort of computation or the output of that, and the computing party may not want to reveal that. In this case, this is a two-party secure computation scenario that I show in this graphic, but it's not specific to this. It can be a single party or it can be multiple parties. So the requirements for zero knowledge and secure computation are not required, but they may be present. And typically in a secure computing environment, there is a lack of trust in the computational setting, whether that means like it's a network level adversary, a computational adversary as in the person doing the computation, or if it's done on, or maybe you don't trust the hardware in case of like, you don't trust the hardware that the computation is actually being performed on. In either way, there is an adversary that exists in our situation that threatens the confidentiality and the integrity of that data. Solutions can exist in both hardware and software. We'll be discussing which of those, and I only have one, which is like something like Intel SGX or trusted execution environments that are built in hardware. And we'll also be saying how that software security is achieved. And as well as for secure computation, the threat models for specific secure computing protocols vary greatly, and they change based on the solutions that you use. What may be considered secure in one setting may not be in another, and it depends very heavily on what your use case is. So, in some use cases it's okay to leak some information, in some use cases it's not okay to leak any information, right? So, to give a brief overview, talking about multi-party computation. It can be considered a software-based security protocol. The security reduces to a cryptographic primitive used. In many cases, people use Shamir secret sharing, and we can actually reduce some of the security to the mathematical properties involved. And in this case, what happens is we have multiple parties that will perform a computation, and the computing parties gain no knowledge of the inputs to a specific circuit, right? So the input data in the beginning is split and then shared across to all these computing parties. And at the end, it's then reconstructed at the end by somebody. And at this point in time right here, this is the only point in time when any data is actually leaked. So in that case, we're not leaking any data during the circuit computation, but whoever reconstructs the output of that circuit will actually learn some data. In a trusted execution environment situation, there exists hardware. It's a hardware-based security protocol. which essentially means that the security reduces to the safe implementation of an enclave or a specific dedicated part of a processor. It literally exists as just a separate secure, in quotes, secure partition in silicon. Most implementations of T's are vendor specific. I give some examples here, which are like something like Intel, SGX, AMD PSP, and ARM Trust Zone. It requires a client API to communicate with the enclave. So if you can see in our diagram here, we have a client API which will communicate with the processor itself and allow the application to be executed inside this enclave, inside this secure part of the processor. There's problems with this, and we go over those as well. But essentially, we're going to have an operating system that runs directly on the processor itself for that execution environment. And then it will perform whatever API call you tell it to perform. In this case, they can be function specific, so it doesn't have to be some generic, it can execute anything, but it, there's things like hardware security modules, which are also forms of trusted execution environments that may do things such as key generation and signing or encryption dedicated to a spot. And these are in wide use today, but some other things like SGX may not be in more wide use than, say, a TPM or HSM, like I said. So now we can get into the meat of what I'm going to be discussing here. Fully homomorphic encryption. So it is a software, you could say software-based security protocol. We can reduce the security to hard lattice-based cryptographic problems. The most practical implementations reduce to learning with errors, which is actually a quantum-resistant problem. So if there exists a really strong quantum computer, this is incapable of being broken by that quantum computer. So FHE solutions exist for both single and multiple parties, which means like we can have a single person. When we have this in our diagram here, we can perform a function, so like a circuit evaluation here. We can have a single party perform that function, or we can have multiple parties perform that function, and in which case that would be something called multi-key FHE. So in this case, in fully homomorphic encryption, the function is computed directly on our ciphertext. It's not computed on the plain text. So we can actually encrypt some data, and if we look at our diagram here, we can take some plain text M, pass it through an encrypting function and get the encryption of that. So we have a ciphertext here. We can evaluate any arbitrary function f on this, and the output is the function computed on the plain text itself. It would be the exact same output had you performed the function on the plain text there. So it's, in short, it's the equivalent of performing the computation on the plain text, just encrypted. What we can refer to this as is, and frequently when we talk about homomorphic encryption, we say things like the plain text domain or the homomorphic domain. What that means is, when we say we compute something in the homomorphic domain, it means we compute some function, some circuit or function while the data is encrypted. So the data that we're computing it on is encrypted. So that's how that works. There's two keys that are used, typically, and depends on the scheme that you use, but in the schemes that we have worked with, we have two keys, and we have an encryption key, which you're familiar with symmetric encryption or public key cryptography. We can encrypt some data and then decrypt some data. And our computation key enables the computation on that encrypted data. So to actually perform this evaluation function here, homomorphically, it requires that you know the computation key here, okay? So, briefly going over some pros and cons of multi-party computation. Circuit designs with MPC are relatively straightforward. They can be constructed with Boolean logic gates. Debugging is also straightforward as well. And it's very clear. You can just perform a reconstruction at any moment in time whenever you're in the middle of your circuit. Say you're designing your circuit and you don't know why you have some value. Well, you can just reconstruct what you have at that moment in time and see what it is and do it. I notice I'm not saying it's easy, but it is straightforward. You can just pretty much say, give me this value. and reconstruct it and do whatever, and you can get that information. The proofs reduce to relatively simple secret sharing schemes. The proofs for those are, I say, relatively simple. Mathematically, they make more sense than, say, something very complex, you know. But some cons of this. Many constructions require additional zero-knowledge proofs for security. So, for example, threshold ECDSA, which has recently amassed some really cool following, and I do think it is very cool, but it is kind of difficult because you actually have to include some, you know, relatively simple zero-knowledge proofs to ensure that the protocol is secure itself. So the protocol does not just include Boolean logic gates, it also requires zero-knowledge proofs in there. Branching is also either impossible or makes it really complex to perform. So when you perform some MPC operation, it's going to require a ton of complexity just to be able to perform some branch, if you can perform that branch at all. And security-wise, operations are still performed on plain text data, although split. You know, depending on what your threat model is, if there's a collusion adversary, this may not be preferable to you. So if that's the case, this may be sort of a not so great thing to use. Now, the biggest problems with MPC come with scalability. Complexity grows linearly with the circuit at best. That also you also then have to include zero-knowledge proofs, which can add quite a lot of interactivity between the parties involved. And network overhead is very, very large. Depending on some schemes may require exponential communication. So if you have 3 parties, it would require like 3 to the 3 communications back and forth. There's a huge liveness requirement. An offline node can block the entire protocol from continuing, so you'll have to wait for that one party to come back online to perform something, which isn't great. And any network latency can have absolutely horrible effects on these protocols. It will pretty much cause, you know, if you have to wait 10,000 milliseconds to communicate with one party, well, since it's exponential, you have to talk to them many times. It's, you know, a few thousand milliseconds that you have to continuously wait to finish the protocol. So now, moving on to trusted execution environments. Circuit design is also relatively straightforward. It's not necessarily like a circuit like you're used to hearing with zkSNARKs. But it uses a very similar API to what you'd normally just be developing with any other library like OpenSSL. It's easier for your regular developer to look at and reason about and build on. Scalability, computation only requires the liveness of the computing party, really. So you can encrypt some data, send it to the computer that you want to compute on, and it can perform some computation inside this environment. There is also some network latency there, but we'll dump into that soon. Debugging is quite complex on SGX, or really any enclave, unless they build a specific interface for this, which arguably might make it more insecure than it already is. There is no way to really just peek into an enclave and see what's going on. You have to provide a ton of print statements and just really see what's going to happen in the enclave and then pull it out and see what's going on there. There's no way for you to look inside the enclave and see what's happening in comparison to something like a software-based protocol where we can, you know, just reconstruct it, like I said, with MPC and just see where we are in the current state. That's just not possible with SGX. So you have to print a lot of data, provide a lot of debug statements, and just try to figure out where a problem is. It would probably be easier to construct it outside of SGX and then move it on the inside, but sometimes that's not possible. Security. The reductions, if you can call them that, are basically the difficulty to exploit hardware, which, as we've seen in the case of Spectre, Meltdown, especially Foreshadow, these just aren't that secure. As much as everybody wants them to be secure, we wish they could be secure. Unfortunately, they just aren't that secure. The attack surface for modern processors is absolutely massive, and if you talk to researchers in this space, while we are confident that eventually someday we might find something and build something that can withstand a lot of attacks and scrutiny, there will inevitably be a break in it, and that's just my opinion as well, but also I think the opinions of many researchers working in this space. For example, Foreshadow, which essentially allowed the researchers to attest to any computation for the keys that they leaked from SGX. That was a massive break. Another problem is that it doesn't really work well with trustless technologies. You obviously have to require trust in the vendor that Intel not only is manufacturing it correctly, that they're not hiding backdoors in this as well. And given what we know about the Intel management engine, this also seems like a kind of bad assumption. We can't trust that vendors are going to do the correct thing all the time. There is no working open source implementations as of yet. Intel has worked a little bit to open source some of their technology, but it's still, none of it is really open source in the true meaning of the word. And any hardware updates still require actual hardware replacement. I can't just update my CPU easily, nor can you get your stakers or miners or whoever to update their CPUs easily. It's more easy on, say, you can still deprecate some old process, but that means you have to get everybody to spend, upwards of maybe $1,000 to a few more $1,000 just to upgrade their CPU to fix a security vulnerability. Not to mention, there is no way of knowing if anybody actually exploited their machine. That would require some weird oracle that I also don't think is possible. So now we get to jump into FHE. Circuit design is also very, very easy to do. In this case, things can be constructed with Boolean logic gates. The talks before, Isaac and Harry gave great introductions to circuit design there. And this, if you're starting to reason about how to build logic gates and circuits in SNARKs, you can probably easily figure out how to do this as well in FHE. As Isaac put it, the SNARKs don't necessarily have bit stuff. So you have to use actual mathematical operations to perform this as well, but FHE actually provides a nice interface into using bit stuff. So if you like bit stuff, then you'd like FHE. But there also exist schemes that don't also necessarily require binary logic gates. You can also use integer operations, and we'll be talking about approximate arithmetic here in a second, which there are schemes for that as well. Security, the operations are performed directly on the ciphertext, and it requires a computation key to perform the operations itself. So this can actually add a lot of great value to a protocol where you can grant access to who should actually be able to compute. It's not just anybody, it's who you designate access to, but this also has downsides. We'll talk about that here in a moment. For scalability, like I said, it can be performed with a single party or multiple parties with multi-key FHE. And it only requires the liveness of the computing parties, right? So you can send some data to that person and they can compute it and send it back, but beyond just sending the data, there isn't necessarily any interaction required between the two to perform something. However, branching is also impossible, or it requires really complex protocols at the current moment. So I'll show a diagram here in a moment about that. So I'll leave that little discussion here for a little bit later. A big problem with FHE at the moment is that since homomorphic encryption is inherently malleable, the best security achievable is CPA, chosen plain text attack security. Typically what you'd want is CCA security for anything in the real world. But the highest we can achieve is CPA security. I'll get a little bit more into that a bit later. But bootstrapping, what bootstrapping is, just to give a very brief overview on it, it gets really technical really fast. But to actually perform this computation, like I was saying, it requires the computation key. That computation key is what is an encoding of the actual encryption key. So when you perform a fully homomorphic encrypted operation, what happens is you use a bootstrapping key that would be called that's also called the computation key. But essentially, as you perform operations on ciphertext, what you call noise, like you have to imagine, like if we're speaking about radios, or radio signal. As you go into a tunnel, you may lose signal and it becomes more noisy and you hear more white noise. Very similar things happen to homomorphic ciphertext. As you perform computations, noise grows on the ciphertext, and the more operations you perform, the less you're able to do to the ciphertext. Eventually it hits a ceiling or a threshold where no more operations can be performed and the decryption is not possible anymore. What bootstrapping allows you to do, this was created by Craig Gentry in his seminal thesis in 2009, which gave us the first practical, or not practical, but theoretical FHE implementation. Essentially, it encodes the private key of this FHE scheme and then allows you to homomorphically perform a decryption. And this gets really complicated and why I'm not diving into it a lot, but it performs a homomorphic decryption while the data is still encrypted, and then it re-encrypts it. So that way it reduces all the noise and refreshes the ciphertext and gives us a nice new ciphertext that we can perform any operations on. That's why we can perform any arbitrary function on that. So the following, when you encrypt or when you encode that private key, like you can literally think of a computation key as a homomorphically encrypted private key of that encryption key, right? So that's called circular security. Matt Green has a fantastic blog post about this. I have a link in the presentation on an upcoming slide. But if you want to learn more about what circular security is, you can go on Matt Green's blog, and he has just a fantastic write-up about it. Another problem is ciphertexts are extremely large. 16,000 times expansion factor in TFHE. That's what we implemented in Nucypher's new FHE. Computation keys can also be large, around 100 megabytes in TFHE as well. And performance speeds are kind of slow depending on computation environment. However, we're going to be discussing all these cons in the next little bit here and say what solutions we have to this. So not all hope is lost. Not everything is bad and broken. There exists great research on how to actually solve this and what we can do to actually make it usable right now. So we'll go into circuit design. Like I said, branching would require pre-computed values or interactivity between parties. This kind of logic, if this, if true, do this, if false, do this, absolutely not possible. To do that, it would break chosen plaintext attack security. Like clearly, if you have some sort of logic that says, if this variable is this, then do that. Of course you can't do that on encrypted data, right? It's encrypted, you don't know what the data is. However, compilers are also being used to create easier built circuits. Okay, so very similar to what you would have with like SNARKy.js or other implementations for SNARKs. We have compilers that are being developed to actually make it so easier to build this stuff. In fact, one of our hackathon winners at ETH Denver, they were called Trustless Health. They implemented a WASM interpreter to FHE logic gates, which was exceptionally cool. So you could write your logic gate, your logic in Rust, compile it to WASM, and then interpret the WASM to perform the homomorphic operation. Very cool stuff. Chris Pikert also has great research on his paper called Alchemy. It's more of an academic project. It's called a language and compiler for FHE made easy. I have a link to that there as well, and also a link to our hackathon winner there. Various schemes exist for different uses. So if you want a different type of circuit that is different from, say, binary logic gates, then you can also use something like Hien, which is great for machine learning. It uses approximate arithmetic, which I'll basically just describe as like, say, you don't need an exact answer to some mathematical operation. You just need something near it, approximate to it, so that you can, perform some operation like machine learning or neural networking, right? TFHE uses binary operations, and say you want to do both, but you don't want to use different schemes. Well, fantastic, there's a framework for this called Chimera that is currently kind of out there and getting some notoriety right now that we're also looking at. It allows you to have interoperability between Hien and TFHE, so meaning you can go between the different schemes and perform computations in either. So we'll get more into the security now. FHE is inherently malleable. Anyone with the computation key can perform any operation on the data, right? So only the encryption key holder can decrypt, but So since we have chosen plaintext attack security as the highest achievable form of security here, there exists also leveled FHE, which enables us to actually achieve CCA security, which may be more preferable, right? So essentially what it does is it limits circuit depth and prevents some arbitrary computations, but you're essentially saying, I will only ever do this circuit of this depth, but no more computations other than that. And we can actually form CCA secure protocols and schemes from that. And also zero-knowledge proofs can be used to prove correctness in the computation to prevent malleability. So we can, theoretically, we may be able to say, are you sure that you performed this one circuit, right? So the example I always give is, say you want to perform a computation on 2 encrypted numbers and you want to add them together. Say 2 plus 2. We may get the output of 4 and that's what you expect. However, because you can perform any computation, you can do 2 plus 2 minus 1 plus 1. And it simply gives you the same answer, but did you ask for that? No, you just want 2 plus 2, right? So we may be able to provide zero-knowledge proofs to prove that the computation was the correct one, and that's something we are actively researching, and we need to learn more about that and see exactly how that can be utilized, but we are working very hard on that. Bootstrapping requires the weak circular security assumption. Leveled FHE does not. If you do that, I have Matt Green's blog on that, so if you'd like to see that, definitely check that out there. Leveled FHE actually doesn't require bootstrapping at all, since you can build a circuit that will work for, or build a scheme that will only work for this one circuit. You can do that. And then you don't actually need the bootstrapping part, but you know, ciphertext size may vary and we're getting into weird realms there. Ciphertexts are extremely large. So as you can see here, 1 megabyte plaintext is approximately 16 gigabytes of ciphertext. That sucks. But all hope is not lost. Ciphertext compression also exists. I have some examples of a poor graph that I pulled off of a nearly dead PDF. It looks like there. But essentially what we can do is we can, before we perform a homomorphic evaluation on that data, we can actually encrypt the data using a generic stream cipher. Like, you know, you're probably familiar with this as Cha-Cha-20, right? But we wouldn't use that. But we could use an FHE efficient stream cipher to encrypt the data symmetrically before placing it in the homomorphic domain and doing computations on it. What that means is we can encrypt the data before, as in the plaintext domain, then as it goes into the homomorphic domain, it gets encrypted, say with like a public key, and then gets evaluated using a just homomorphic decryption. So you do the homomorphic decryption on the stream cipher encrypted data, which will roughly keep it the same size as the original plaintext data. So it allows you to, you know, keep the ciphertext small in storage, but expand it in memory, which is great depending on what you need to do. Heian potentially only has a 40x expansion, which would be much, much, much better, but that's kind of research level right now. We're still evaluating that, and also Heian, the authors, we're still trying to figure out how that may be used. Performance speeds can be improved from GPUs, ASICs, and FPGAs. NewFHE has increased performance by 100 times in the GPU. So you see TFHE normally has 13 milliseconds per bit. We actually achieved that speed up to 0.13 milliseconds per bit, making us, as far as I know, the fastest fully homomorphic encryption library available. So that's pretty cool. And on the GPU, we also have NTT, so that's with FFT. We can also use NTT, and still roughly 0.35 milliseconds, same speed as CUFHE, which is another FHE library. But of course, this can also be improved with GPUs, ASICs, and FPGAs, which is something we're interested in. So that's the talk. Obviously, a ton of extra information, so if you have any other questions, ask them. Please see me after. I may even do a breakout session if anybody's interested in talking more about this and explaining some of these concepts. But feel free to go on our website, nucypher.com, join our Discord, email me, tweet us, and definitely look at NewFHE. Thank you.
We have time for a few questions if there's anything anyone wants to ask right now. Otherwise, we can take it to the breakout session afterwards, maybe.
Hello. So I have a question on the decompression. So this means that have you implemented this the Trivium cipher in the hybrid homomorphic way?
Your question is if we have actually implemented it yet? No. This is all, if you read a lot of the FHE papers, they explain how to actually achieve this compression. But it's not, I'd say it's outside of the realm of theory, in my opinion, that what we need more so is the existence of an FHE efficient stream cipher and to prove the security of those ciphers. There's some examples here in this paper, and I have that link there if you'd like to look into that. But essentially you just need to implement that. It's relatively straightforward bringing that out of the papers and into the practical applied realm. But it seems pretty straightforward, right? You just encrypt the data and then pass it along into the FHE cipher, and then it can then perform like a decryption circuit in the homomorphic domain, perform the computation, and then you're done. It just expands into memory. Make sense?
Where we also try to implement AES as homomorphic circuit, but it takes a very long time.
Right. AES does take a long time, but that's also because it's not an FHE efficient stream cipher. So there's been research into finding something that is much more efficient than AES, right? As far as I know, actually, we have sped up AES computation in FHE actually quite a bit now, but it's still, not that practical. We'd much prefer something like Crevium 13 or something.
All right, thank you very much.
Thank you.
And let's bring up our next speaker. Just going to prepare here. All right, next up we have Alex from Matter Labs, who will be talking about SNARKs versus Sonics. Please give him a round of applause.
Yeah, you've seen that in the schedule. It was a little bit also about the information of the Matter Labs itself. I will keep this part short. Luckily for me, a view from SNARK already explained a lot about all the solutions which are possible to make for level 2 networks, for transaction aggregation, for batching, and some other forms. I will just say what we do exactly. So right now, we're working on a level 2 solution, or just sidechain, how people call it, which is using zkSNARKs for transaction aggregation and scaling of the public chains. And public is important here. We need existing primitives. So we use what we have in Ethereum right now. Our goal is universal solution in some sense, and I will speak a little bit about it later. Initially, we finalized our set of features for a first version about like 2 weeks ago. Would be transfers, would be DEX settlements in the form of atomic dependencies with arbitrary chains, and state channel opening, funding, and closing without escalation, so for best case scenario. We want to move in the field of privacy to hide at least the transaction amounts, but for now we optimize for efficiency, so this is not in the first version. Also, decentralization is important. For such a level 2 network, it will be required for someone to aggregate the transactions. And we want the party who would have to aggregate these transactions, which can be called in different settings, like in Plasma, those entities are called operators. We call them validators, and it doesn't matter, they just make the proofs. We want those parties to be more than one, or more than one finite set of entities which are known upfront. So we want to have wider participation for this network. But in principle, we work in a both practical part and just some fundamental part to have further progress and direction for advancements. And my personal goal, or more or less what I want to do, is to have some form of arbitrary, kind of as a smart contracts in a level 2 layer. But for this, we need recursion, and I will not stop on this today. So universality is important, and that's why I actually presented it here today first time. We call for initiative for more or less universal zkSNARKs, for now, standards, for all the public chains, in a sense of tooling for users to design circuits, backend for proving, so those can be interoperable, like reference verification contracts, reference batch verification contracts, and all this part. Maybe some reference functionality for some kind of networks. And if you want to know something, please use this email. There is no website, so just email, and we will answer your question directly. So why universal? Universality is important because we work in a public chains, and even while you can do compression of transactions efficiently, so you can just prove a lot of transactions, one state transition from another state route to another, you need still to care about the worst case scenarios. When someone needs to reconstruct the whole state from some parts, and to be able to have the procedure of movement funds back to the main chain when there is no cooperation from the operator. This can be more or less eliminated if there is some form of decentralization, but it's not final. So for this part, I will just give actually the concrete numbers. Every transaction which is aggregated by us using zkSNARKs will consist of two parts. One is how much you pay per verification, how much you pay for public data, which is required for now to solve the data availability problem. And for our case, if you go full scale, fully filled blocks, payment will take 150 gas per transaction just per verification. Exchange will take, well, actually twice more, but let's put some margin for now. And now for data availability. Now, even without the privacy, which will require additional costs, it will cost 750 gas per public data to be able for every participant of the network to reconstruct the state for worst case scenarios, which we should always care about in a public and decentralized networks, when some party just refuses to cooperate. And yeah, it's already a lot. If you want to put 1,000 transactions, you multiply it by 1,000, already quite a lot more and more and more. You take also network capacity, and if you use 6 million proof for Starks, you take more network capacity, and then we have another cryptokitties, or whatever. And actually, if you just go into there is research on this, how much data is transferred between the Ethereum nodes, how much more you can push, and it's actually just much more difficult than just say, let's just reduce it 10 times. Fortunately, it also depends on the network level, and if you want to have the decentralized network and keep the Ethereum decentralized, you cannot estimate that every node which actively participates has a gigabit of network capacity. So we cannot estimate this, so just saying that let's put the price for data 10 times less is not going to work. So that's why something universal is more or less ideal, so you can have a wide functionality for as many users of the network as possible, whether it's taxes, payment solutions, state channels, what L4 is working on. So you always pay, per any proof of any transaction aggregation, you pay the fixed price, no matter how many transactions you actually have the block, and how many transactions actually just dummy transaction we choose for padding. So this price is fixed, and you still put always the same price, whether it's padding transaction or not, for public data. So if your blocks are underfilled, it actually hurts the network in both levels. So if you don't have the network, we can operate at the maximum efficiency and simultaneously be properly filled. So that's why there is a need for some universality. You can just scale efficiency. There will be just cryptokitties again. But best part is actually much more interesting, especially for me, and I think for people who actually join us here today. So for Sonics, I'm going to repeat the Sonics is another proof system, as it has a common reference string. Yes, it has a common reference string. It requires trusted setup, but this trusted setup is first of all universal. You run it once, and you can use it for any circuit up to the given depth. And it's updatable. If you don't trust the previous trusted setup, you contribute on top of it, and let's say you trust yourself. And please, I don't take any credit for any implementation I make. I make improvements, I make new primitives, but all credit should go to the original people who made this idea, so please, their names. Also, if just to show how Sonics and standard SNARK like Gross 16 are different. Let's say you want to play a game, a card game. For Gross 16, you take a deck of cards, you shuffle it under the table, give it to another participant of the game, you shuffle it under the table, and you get the deck on the table. And you play the game with this deck. And for every game, you need, and you DAC. So you need to go over all this procedure again and again. For SONICs, you shuffle the DAC, you give it to another entity, and at the end of the day, you get the shuffled DAC in the table. And then you magically clone it and use it for a game. And if you want to play another game, another kind of game, for example, just another round, you clone it and you play it, and you only need to do a shuffling once. Well, up to games which require only 52 cards, for example, to play. So both of these proof systems can potentially start from rank 1 constraint system. Also, SONICs use the multiplication gates and linear constraints in their paper and in the description, but they can all start and those can be reduced. Main parameters for gross 16 is just number of constraints, as many people are familiar with. For SONICs, in the paper it describes that like the most important parameter is the number of multiplication gates. Actually, number of linear constraints is also important. So here you have to care for more numbers. And well, implementations. So since SONIC implementation is not there yet, but the implementation of the gross 16 in terms of prover and verifier and batch in on-chain verifier is there. So we can hope for something like 200 gas per proof in the batched mode of 5 proofs checked at once, if there is one public input, for example. Now about the efficient implementation. Everyone knows that for gross 16, or in principle, you want to run some FFT, so you want the scalar field with a large number of roots of unity. Your prover will work in both small and large groups, and G1 and G2 usually called. The implementation is available. A lot of operations are highly parallelizable up to the very large degree. So can be done efficiently. You can scale it to more CPUs if you want in your large beefy server, if you want to prove the large circuit over a small time. With SONICs, operations are parallelizable, at least a large share of them. Maybe except of one, but it doesn't take a lot of time, as I tested. The prover implementation requires only multi-expansions in G1, which are usually like 4 or 5 times less expensive, which is potentially also good. The problem is that for FFT, for some polynomial multiplication, which you need for SONICs, well, the number of multiplication gates, I will show how it's related to the number of constraints, but potentially SONICs limit your circuit size for a given scalar field, unless, well, because you need efficient polynomial multiplication, for which you just need an efficient FFT. So just concrete example of the conversion. If you go to the MIMC circuit, standard one, just open the Bellman repository, find one. If you convert it, originally it has 644 constraints. If you convert it, you get 968 multiplication gates. I didn't put the linear constraints here, I actually forgot about it. And roughly the conversion is trivial. You take a rank 1 constraint system constraint, you convert it into 3 linear constraint plus a multiplication gate. And also to allocate any variable, private or public, you need like 1/2 of the multiplication gate. So this formula is more or less universal. So you see it's actually just grows with a small factor, but still. Then there was a part of the paper which was much more difficult to understand, which was about help procedure, and help procedure, whether the proof is succinct or not. So I will go into these details just one step after another. The same way as more or less structured in the paper for just understanding of the audience. So let's say there is no bunching, there is no requirement for succinct proofs, it's just one proof which someone needs to prove. So prover does 3 polynomial commitments plus a signature of correct computation. Fortunately, the signature of correct computation, its verification in this naive form requires a number of steps, which is equal to the number of multiplication gates. So the verifier in the setting is not succinct. So we need to go further. What was called the help procedure. You can make some entity an untrusted helper, so it can be anyone. This entity can aggregate M proofs and M signatures of correct computation and produce 1 signature of correct computation. So basically you reduce the verification work from M by N to just N. Still not succinct. The succinct procedure called unhelped. Yes, you can make the signature of correct computation succinct, also for some trade-offs, such as increase the number of multiplication gates up to the 3 times. We will go into it later. And yes, your verifier is now succinct. What you can do, you can mix and match. You can take both. So this most likely is going to be an optimal procedure. So you make m independent proofs over one circuit. You aggregate the signature of correct computations. And then you transform the signature of correct computation as a succinct form, and you get the verifier whose work is actually still linear in the number of proofs which you need to verify, but now the signature of correct computation is at least succinct, so this one is more or less like a batch verification of the SNARKs, the standard Gross16. Okay, now benchmarks, which were not in Paris, because some people could have seen this presentation kind of in Paris. This is a concrete example, a test circuit with few SHA 256 rounds, which just leads to this number of multiplication gates and linear constraints. I mean, one rank 1 constraint will transform in 1 multiplication gate plus 3 linear constraints, which is quite obvious. And my machine, just a laptop, modern MacBook, 12 virtual cores, 6 physical ones, but virtual cores actually do help when you run the procedure. For Gross16, it's 0.6 seconds per proof, so it's for 5 proofs, let's say 3 seconds. With SONICs. Single proof with just production of the proof itself, plus what's called the advice, a commitment to the signature of correct computation, as unfortunately 9 seconds. The part which is called the helper, the untrusted part which anyone can run, as something like 12 seconds to aggregate 5 signatures correct computations, and this work as linear in number of computations you want to aggregate, so it's not amortized. So the reduction, just plain implementation of the reduction procedure, even also we made a good progress on how to actually implement it. It's not in the code yet. So let's say the worst assumption from the paper, which will increase the number of multiplication gates 3 times. So we just scale all the results previously by 3, which is a good assumption actually. And so we go to the synthetic part of the benchmark. Part of this is synthetics only for proof calculation part, for succinct signature of correct computation, which requires permutation arguments, 3 permutation arguments, grand product arguments, and well-formatness arguments. Everything is from the paper. If you want to go there, just the same names. For those, not the most efficient implementation yet, because it just has a procedure which can aggregate internal parts. It's around 60 seconds, which let's say 30% can be shaved easily just by aggregation. So in total of 226 seconds, it's almost 80 times more. Quite unpleasant for now, but now let's focus that we optimize not for time, but for a price per proof. And for optimization for a price per proof, because you can always scale all these proven techniques with, well, up to, of course, some given degree, but quite far, I would say. You can just spend more computing power on it, and just basically will be more per 1 proof if you want to fit it at the same time. For this, well, we work on the parts which should help us with this. Like before it, there was a whiteboard session about the implementation of GPU provers with some benchmarks and like very early steps on. So my estimate from what we have already, without any professional GPU design experience, we could already achieve up to twice the performance in multi-exponentiations. And multi-exponentiations is a procedure which is present in both Gross16 and SONICs proof systems. So it takes in SONICs 70 to 80% of the prover time. Those can be efficiently sped up by GPU, and speed up here, either you spend less time or you need less resources in terms of price to fit into the same time window. So here, everything which is called speed is actually optimization for a price. So if you say that we achieve what we have as, well, 35 seconds. Still quite a large multiplier, but first of all, one should remember why we want to have SONiCs in the first place. This is a part where you don't need to have a trusted setup per any user application. As I mentioned, I want to have some kind of smart contract logic on in layer 2 chains. For this, some crypto primitives are needed, which are not yet available in Ethereum, and we work for Ethereum as a level 2 chain, and that's why I say that there are limitations. If the primitives are available, if recursion cycles are available, why the set of curves is available, well, we can verify the sonic proof inside of the circuit, with the circuit itself being either sonic, gross 16, or something else, so we can efficiently mix and match and just provide the functionality which would be interested for the end users. Either we use sonic, so the top level is GPU, so we just have users who prove their private smart contracts using the CPUs. Just the implementation should be done, tested, and what I actually think is over this year, maybe next year, there will be another step further in common reference string succinct proof systems. So I expect the next implementation will be even more efficient, and we already see that, well, yes, 25 times more, but still manageable. And the worst case, because we still even, work for public blockchains, we will need to go for worst case scenarios, even if the SONiCs are not that efficient. We have the plan, just for what we do. Thank you. I try to leave more time for questions if someone has. Talk is quite involved, but I hope that it's a Zero Knowledge Summit. People know what we will be talking about. So please, anyone.
Any questions? Nothing? One in the back?
Can you detail a bit more what's the difference between the multiplication gates representation that you use and R1CS, and how complicated it would be to translate?
Well, first of all, the translation procedure is not that difficult. In R1CS, you basically have the multiplication of two vectors of variables plus addition. Multiplication of linear combinations, element-wise. These parts, each, usually represented A multiplied by B minus C is equal to 0, where A, B, and C is linear combinations. You just make one linear constraint in SONiCs, which is for A, and you make a new variable, which will represent all this A combination. You take the same for B, you take the same for C, and now you have basically AB equal to C, which is your multiplication gate. So the transformation procedure from R1CS to what SONiCs use in the paper for multiplication gates and for linear constraints is trivial. Linear constraint is just, it's linear constraint. Multiplication gates is just three variables, A, B, and C, which are A multiplied by B is equal to C, but not in terms of linear combinations, but in terms of individual variables in your constraint system.
Any other questions? Then let's thank our speaker again, and we'll have a small announcement from Anna.
All right, so that concludes this part. I think we have a half-hour coffee break right now. And then after that, we have the SNARKs with pen and paper workshop. A lot of people have been asking us about that. That is limited, but mostly due to the size of the room. So if you really, really want to go, I would actually go and sit now.